So, welcome to this lecture series. In our last lecture, we have seen that if we consider a vector space V of dimension say n and V star with the corresponding dual space, then for any order basis alpha 1, alpha 2, alpha n of V, there exists a dual basis f1, f2, fn for V star. Of course, we have seen in last examples, when we consider a dual basis f1, f2, fn of vector space V star, we have also found a basis alpha 1, alpha 2, alpha n for the corresponding space V. That we have checked through the numerical examples. But in general, we have not answered the questions if V be a vector space defined over the field capital F and V star be the corresponding dual space, and if f1, f2, fn be the basis for V star, then the question is whether for each such basis is there any dual of some basis for V. I mean this each f1, f2, fn, this basis for V star is a dual for some basis for the V. That is the question, please. I mean, does there exist alpha 1, alpha 2, alpha n in V which will be basis for the V? Now, to answer these questions, we can proceed like this. Consider for each alpha belongs to V, a function L alpha on V star defined by your L alpha operating on F equal to F of alpha. So, this is basically, this implies it is a function. So, L alpha is a function from V star to your field capital S. This function we can check, it is also linear function. I mean for f1 and f2 belongs to V star, we see L alpha and C belongs to say field capital F, L alpha of C f1 plus f2 equal to, we have C f1 plus f2 operating on alpha, which is equal to C times f1 of alpha plus f2 of alpha. So, this is equal to, we have basically C times L alpha f1 plus L alpha f2. So, this implies this L alpha is a linear functional on V star. So, for each alpha we have introduced a linear functional L alpha like this. So, this implies that L alpha belongs to V star star. This is called the double dual space, please. V star star is called as double dual space for vector space V, that is dual of V star equal to V double star like this. So, we see that for each alpha one can introduce a linear functional L alpha defined like what we have already done. Now, my claim is that a function from alpha, a function psi from v into v double star defined by that psi of alpha equal to L alpha, psi of alpha, this one is a isomorphisms from V into V double star. So, the way we have introduced L alpha, and then I am defining a function psi from V to into V double star defined by psi of alpha is equal to L alpha. Now, my claim is that this psi is an isomorphism from V into V star, that is claim psi is a 1-1 linear transformation between V and V double star. Since V is finite dimensionals, so V star star is also finite dimensional, and dimension of V equal to dimension of V double star. Consequently, if I somehow prove that psi is a 1-1 linear transformation from V into V double star, then psi is also 1-1 onto linear transformation from V into V double star. That is, psi will be an isomorphism from V onto V double star. Okay. Consequently, 1-1 implies onto also. So, first I have to prove that psi is a linear transformations. So, let us see how psi is a linear transformation. Psi is a linear transformation LT. For alpha and beta belongs to V and C belongs to capital F, we have psi of alpha plus C beta equal to L of alpha plus C beta, L of this ones. Claim L of alpha plus C beta is equal to L alpha plus C times L beta. For F belongs to V star, L alpha plus C beta of F equal to F of alpha plus C beta, which is equal to F of alpha plus C times F of beta, which is equal to L alpha plus C times L beta, this operating on F please. So, this implies that L of alpha plus C beta equal to, we have L alpha plus C times L beta. So, this implies psi of alpha plus C beta equal to L alpha plus C beta equal to L alpha plus C beta L beta is equal to, I have psi of alpha plus psi C times psi of beta. So, psi is a linear transformation. For alpha not equal to 0, if psi of alpha equal to 0 implies that L alpha equal to 0. So, L alpha is basically linear functionals on V star. So, this is equal to 0 implies that L alpha operating on any f equal to 0, which is equal to f of alpha for all f belongs to V star. But we know for alpha not equal to 0, one will get at least one f such f on V star such that f of alpha not equal to 0. Already we have explained in our previous lectures, if we consider a non-zero element in V, one can immediately find out a non-zero linear functional f on V star such that f of alpha not equal to 0. So, based on that we have a non-zero linear functionals. So, this implies there exists f for which L alpha f equal to f of alpha not equal to 0. This implies that, so for alpha not equal to 0, L alpha cannot be equal to 0. L alpha cannot be equal to 0, please. I mean 0 linear functionals. So, this implies that your psi is 1 1, because the null space of psi is only 0 subspace, please. Psi is 1 1. So, we have psi is a 1 1 linear transformation from V into V double star. Since already we have explained the dimension of V is finite and that is equal to dimension of V double star. So, certainly if it is 1 1 implies that it is also on 2, please. So, psi is an isomorphism from V into V double star. Okay. So, we have seen there exists a 1 on to map linear transformation from V in and V double star. So, that is alpha goes to L alpha, we have this one. So, what we have achieved from this? Okay. So, let me clarify this once. See, so we have for any L in V star, L on V star, any linear functional on V star, there exists an unique, I can say there is a unique alpha belongs to V such that L equal to L alpha, because since we have seen for there is a 1 to 1 map between V and V double star. So, whenever you consider element in double star, I mean L is basically element in the V double star. So, definitely there will be element in V. So, for any L in V double star there will be an element alpha belongs to V such that L equal to L alpha, please. That is L of f equal to L alpha of f is equal to f of alpha, please. So, this implies if f1, f2, fn is a basis of V star, then we know if this is the basis for a V star, then there exists a dual basis L1, L2, Ln for V double star such that Li Fj equal to delta Ij, where 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to n please. This is already we know from previous studies that if we consider basis for this space V star, then certainly there is a dual basis L1, L2, Ln for V double star. Again, for each Li there exists alpha I in V such that Li equal to alpha L alpha I. Previous result says that for each Li there exists alpha in V such that Li equal to L alpha I. So, this implies one will get alpha 1, alpha 2, alpha n related to L1, L2, Ln. Now, if L1, L2, Ln is linearly independent, certainly alpha 1, alpha 2, alpha n will be linearly independent, and that is coming as a straightforward because psi is a 1 1. So, if alpha 1 and if suppose L1, L2 are linearly independent and alpha 1, alpha 2 not equal to independent, means they are dependent, you will get a contradiction that psi carrying non-zero to 0 vector place. So, this implies that alpha 1, alpha 2, alpha n is the required basis for V, so that F1, F2, Fn is the corresponding dual basis for V star please. So, we see that if we consider a basis F1, F2, Fn or V star, certainly there exists a basis alpha 1, alpha 2, alpha n V, so that F1, F2, Fn the dual of alpha 1, alpha 2, alpha n basis please. So, we have basically studied what is linear transformation, what is linear operator, linear functionals. Now, we want to see, suppose a linear transformation is given to us, whether these linear transformations can introduce another linear transformations on some spaces. So, we are interested for that. So, that we are basically talking in terms of this is I am talking about the transpose of a linear transformation. Okay. So, before introducing the transpose of a linear transformations, first let us see how to define how a given linear transformation introduce another linear transformation please. Let V and W be two vector spaces over a field say capital F. Let T be a linear transformation from V into W. So, that is T is map from V to W. Consider V star and W star be the dual of V and W respectively. Okay. Let G belongs to W star. D belongs to W star, means G be a linear function on W with G of T of alpha equal to f of alpha. I am considering a functions f basically g of f of alpha is equal to g of t of alpha, please. So, that is f equal to g t. So, I have considered a function which is composite of g and t. So, t is a linear transformation from v into w and g is a linear functional on w star. So, take the g into t, composition of the g and t, then I see that g t is a linear, it is a basically functional, or you can say function here from v to capital F, please. So, I have considered g of t of alpha equal to this thing for all alpha belongs to v. Suppose it is like these things, then the function f is a function from v into capital F. Since t is linear transformation and g is also linear transformations, linear function and linear transformation. So, it is a product of two linear functions. So, f has to be also linear. Okay. So, if I consider f of c alpha plus beta equal to g t of c alpha plus beta, which is equal to g of t of c alpha plus beta, g of t I mean c into this plus t of beta, which is equal to again c into g t of alpha plus g t of beta, please. So, this is a linear functions. So, f is a linear functional on V star. Now, let me define T t a functions which is mapping from W star to V star. See, from the linear transformation T, I am able to introduce a linear functional f, like what I have done it here, and that linear functional f is defined on basically V. So, I can define another function T t which is mapping for each g to any g belongs to W star. I am defining say T t g, and that T t g is equal to basically g into t, please. T t, claim T t is a linear transformation from W star into V star, W star into V star please. Okay. Because for G1 and G2 belongs to W star and C belongs to capital F, Tt operating on Cg1 plus G2, which is equal to Cg1 plus G2 to T. So, this implies that Tt of Cg1 plus G2 when you operating on this alpha, for any alpha belongs to the V, this is equal to Cg1 plus G2 T whole operating on alpha please. This is equal to Cg1, this is equal to according to definition Cg1 of T alpha plus G2 of T alpha. So, this is equal to C G1 C into G1 of T alpha plus G2 of T alpha. So, this implies what? This implies T2 Cg1 plus G2 is equal to T2, I mean T transpose this one, this rule, C times this G1 plus Tt of G2. So, Tt is a linear transformations. Tt is called as the transpose of the linear transformation T. So, Tt is the transpose of T. One can take an examples, say let T is a map from R2 to R2 are defined by say alpha equal to x1 comma x2 goes to say x1 comma 0, that is T of x1 and x2 equal to x1 0, and let G is a linear functionals belongs to basically R2 star and is defined, and G of R2 please, G of x1 x2 equal to A x1 plus B x2. So, this implies your Tt operating on G of alpha will be G of T of alpha, which is equal to G of T of alpha means x1 comma 0, x1 comma 0 which is equal to A x1. So, we will continue with this in the next lecture please.